So in this presentation I want to talk about colour characterisation of a display. Now I'm not going to talk about sRGB or ICC, the International Colour Consortium, or even the problem of how you ensure that different displays in different geographical locations display the same colour, although all of those things are interesting in their own right. What I want to talk about is a very specific problem, which is where you want to display a colour on a display with a specific CIE XYZ specification, and you want to know what are the RGB values you need to drive the display to produce that XYZ. So you need a system that relates RGB to XYZ. And this is a problem facing many research students, for example, in our laboratory and in other laboratories. I want to start off by talking about additive colour mixing. So you'll be familiar with this situation where you shine 3 projection lamps onto a white screen, one shining red light, one green light, one blue light, and you can overlap the lights as seen. Now we can measure the CIE XYZ tristimulus values of these 3 lights. We can use, for example, a spectroradiometer to do that, and you can see measurements on the right hand side. Well, we can use these to predict what the XYZ values of the overlapping region, the white part in the center, would be, because it's simply the sum of the XYZs of the 3 components. Why is this? Well, it simply is a property of how CIE XYZ values work. They're additive. XYZs of different lights are additive when you combine them. But there's something else, which is if we consider that we could change the intensities of these lights, and we call the intensity of the red light R and the green light G and the B light B, and if we express those intensities in the range 0 to 1, you can see that the X contribution of the red light would be 114 times R. 114 because that's the X value of the red at full intensity, and R is the intensity 0 to 1. So if you reduce the intensities to 0.5, i.e. half it, then you should halve the amount of light emitted. So instead of getting X value of 114, you get 57. So this means that there's a linear relationship between the RGB values and the light which is output. And if we take the white in the center, then we can predict its X value, for example, by having 114 times R plus 68 times G plus 40 times B, where RGB are the intensities of the 3 lights represented in the range 0 to 1. So we measure the XYZ values of the 3 primaries. We can then write down the equations on the right hand side, which show how we predict the XYZ values of any overlapping area. And we can represent that as a matrix equation. Notice that compared to the top left, these sets of 9 numbers are transposed here. So you've got 114, 68, 40 going down on the top left, and on the bottom equation 114, 68, 40 going across. So X value equals 114 times R plus 68 times G plus 40 times B, and Y equals 52 times R plus 165 times G plus 15 times B, and so on. Hopefully you're all familiar with matrix algebra. So this 3 by 3 matrix we can call M is a matrix which relates the RGB color space to the XYZ color space. But it implies explicitly a linear relationship between RGB and XYZ. As I said, doubling the intensity of the driver to the light doubles the amount of light which is output. So could we use this very simple equation to characterize our display? Remember, for our display we want to start with RGB and get X, Y, Z. We seem to have an equation that can do that here. Well, yes and no. There are a couple of problems. So here you can see 4 steps on what I call a color ramp, where you've got R equals 0, 60, 120 and 240. G and B are both equal to 0 in all cases, so it's a red color ramp. And if you measure the Y values of these 4 steps, you can see that between R equals 60 and R equals 120, if the display was linear, then we should be doubling the luminance Y. So 2.25 should be becoming 4.5 here. But it's more like quadrupling instead of doubling. And then at the bottom here, 120 R to 240, again a doubling. This 9.54 should be doubled here, and it's much more than doubled. So in other words, the way that most displays work is there is not a linear relationship between RGB and XYZ. So I refer to these RGBs that we can manipulate in software, for example, as being non-linear RGB values. And if we take not just 4 points on that color ramp, but in this case about 14, with R values between 0 and 255, for example, we measure the luminance, we get this visualization of the non-linear relationship between R in this case and Y in this case. So the RGB values that we can manipulate are not linear. That is, doubling the RGB values does not double the amount of light that is output. So because of that, color characterization is a 2-step process. Step 1, we need to convert the non-linear RGB values to linear RGB values. And step 2, we convert the linear RGB values to XYZ using the matrix M. And the matrix M, remember, we can simply write down if we know the XYZ values of the 3 primaries at full strength. And here we need to have, of course, the linear RGB values. The problem is we don't know what the linear values are. But what I would say is that if we did have the linear values of R for our red color ramp, and we plotted them against the measured Y values of those color stimuli, we'd get a straight line like this. Well, yesterday one of my graduate students said to me, "Why would we?" And I said, we simply would by definition. Because by definition, if I say R is linear, I mean it is linearly related to the Y value. Doubling the R value from 100 to 200 doubles the luminance from about 20 to about 40 in this case. But because the scales are different, this one goes from 0 to 255 and this one goes from 0 to about 55, they're not equivalent. So you have a R value of 155 and a luminance value of about 30. But what if instead of plotting the R values against the Y values, like we have done here, we normalize them by simply dividing the R value by 255, so it goes between the range 0 and 1. We plot the Y value normalized by dividing the Y value by its maximum value, about 55 here. So then we get this graph, which shows normalized linear r go between 0 and 1 and normalized y value between 0 and 1. It's still linear, but because they have the same range now, you can see there's an equivalence. 0.6 normalized linear r corresponds to 0.6 normalized luminance. And 0.4 normalized y value corresponds to 0.4 normalized linear r. In other words, they are equivalent. And because of that, we can use normalized y values as a proxy for normalized linear RGB values. Remember I said we don't know what the linear values of RGB are, but we can actually use normalized y values instead of them because they are equivalent. And that's why we talk about using normalized values, not non-normalized values. So we can take our color ramp and we can plot here the normalized non-linear r, these are the values we used to create the ramp, and plot it against normalized y value that we measure for each of these patches. And now we get the relationship between this and that. But remember, on the y-axis, where we've put normalized y value, that is a proxy for linear r. So what we have here is a graph that shows normalized non-linear r on the x-axis and normalized linear r on the y-axis. Exactly what we need. And if we do that for all three channels, we can get graphs like this, which show a very typical power law relationship. So in this case, I've fitted the data with an equation of the form y equals x to the power gamma, and you can see that gamma is about 2.25 in each case. It's a little bit bigger for the red channel, a little bit smaller for the blue channel. But we could use this equation now with the values of gamma to take any value, for example, of nonlinear g here, and use the equation to tell us what the corresponding value of linear, normalized linear g would be. So 0.5 becomes about 0.2. 0.75 becomes about 0.55. This is the approach taken in the GOG model. Not quite, because the GOG stands for gain offset gamma. So gamma is this power term. There's also a gain and an offset. But broadly speaking, you're doing something like this. And you can see that this model fits the data fairly well because many displays have got a power law relationship like this. If you look at the blue one, at very low values, drive values, you can see it's not fitting perfectly, but not doing a bad job. I tend to not use the GOG model in most of my work, and the reason for that is it assumes that you will have this power law relationship. Now, back in the days when I started my research life, when we used CRT, cathode ray tube devices, they all had this power law relationship, and the GOG model worked very, very well. But modern LCD, LED displays, they don't always have this relationship. Sometimes, for example, instead of this gamma relationship, they've got an S-shaped tone reproduction curve, as we call this. So the GOG model doesn't always work very well. Instead, I use something called piecewise linear interpolation. And what this does is take any two adjacent points and simply plot a straight line between them. And so if we want to find out, for example, what the corresponding value of linear r would be, we simply go up here and then interpolate between these 2 points linearly, and that gives us the value on the y-axis. It works pretty well in this case visually. It fits the blue data really well. If you have only a small number of points in your color ramp, then because the distances between adjacent points will be much larger, these straight lines, this family of straight lines, won't be a very good fit for the true relationship. But if you have a reasonable number of points, like 10 or more, as I've got here, it works pretty well. And this is actually the approach taken in another model called the PLCC model, which stands for piecewise linear constant chromaticity model. So with all that in mind, I want to show you now how simple it is to take RGB and predict what X, Y, Z should be. This is my MATLAB code to do it, and this is literally all the code that you need. So you start off with RGB equals, in this case, 110, 56, 203. And the first thing we do is, of course, normalize it in the range 0 to 1, which gives us these values on the right-hand side. Now, these are non-linear RGB values. We've got to convert them to linear values. And to do that, I'm going to use piecewise linear interpolation. I have a function I'll show you in a second called getVals, which I wrote. You pass it the X data here, which I call ramp, and the Y data here, red ramp Y, and you pass it the value you'd like to interpolate at on the x-axis, in this case RGB1, the red value. The ramp data here are 0 to 1, and they are the non-linear RGB values of the color ramp. And the red ramp Y data, they are the normalized measured Y values of the color ramp. Remember, they are a proxy for the linear R values that correspond to these non-linear R values. So we can simply use this function getVals to do the linear piecewise interpolation to get our linear RGB, put them together here to get these are the linear RGB, these here are the non-linear RGB. Once we have the linear RGB, we simply take the matrix M and multiply that by the RGB values to get our X, Y, Z values, 45, 23 and 130 approximately. These are absolute X, Y, Z values, so the Y value corresponds to luminance in candelas per meter squared. And if you're not familiar with MATLAB, you're wondering what this exclamation mark is, it's simply transposing the vector. So the RGB vector is a 1 by 3 vector here. And if you multiply a 3 by 3 vector by this vector must be 3 by 1. So we simply have to transpose it in order to make the matrix multiplication work. So it's literally as simple as that. So for those who are interested, this is my my getVals function, which I've been using for more than a decade. It's a general purpose linear interpolation, not just for use with displays, where you have X values and Y values, and you give it a value, Tx, or values, you can do several at once, to interpolate. So it uses these on the x-axis to interpolate to the corresponding Y values and passes them back. The function only works if X and Y are normalized in the range 0 to 1. But if anyone wants to use that, they can key it in, or if you email me, I'll send you a copy of it. Is PLC better than GOG? Well, it depends. If the display has a power law tone reproduction curve, GOG might work better than PLC. If you have relatively few samples in your ramps that you use, then you also might find that GOG works better. But in many cases, PLC works better. And generally, my recommendation would be try both and see which one works best for your particular display. Generally, some displays are better than others in this regard. If you have a high quality display, you're likely to get better results than a low quality display. And that's partly because of these factors. So these are things that we typically measure in the lab on a display before we even start to characterize it. So if you have, for example, a high quality BenQ display that you're thinking of using, and then you've got your laptop display you're thinking of using, and you're thinking, well, I think the laptop display is as good as this lovely BenQ display, then measure these things and show that it is. And you'll probably find that it isn't. So let's just run through these things quickly. Spatial stability. If we have spatial stability, we should measure the same X, Y, Z values at each spatial position. So we might measure in the center and in the four corners like this and calculate the color difference between these measurements. The smaller the color difference, the better the display. With most displays, they get darker as we go towards the corners compared to the center. Sometimes we measure 5 points like this. Sometimes we measure 9 points. It doesn't really matter. We also measure temporal stability. So in this case, we turn the display on and measure, in this case, the luminance every 30 seconds and plot it. And you can see that the luminance is drifting. It's generally, after a very unstable beginning, increasing with time. And when we get to 30 or 40 minutes, it's sort of stabilizing. So this is quite typical. So what this means is that before you use the display for any work, you should turn it on and make sure it's had 30 to 40 minutes to warm up. The third one I want to talk about is channel independence. If you remember, for our example at the beginning of the red, green and blue lights shining onto a white screen, if we measure the X, Y, Z values of these three lights and add them together, we should get the X, Y, Z values of the white when we measure them. But we don't. You can see here there's a difference. The difference is about 1.6 C-lab units for this particular display we looked at. This is caused because the amount of light output by this channel depends not upon the R value, but also what these other channels are doing. So in other words, the channels are not completely independent. And you remember when I said earlier on, I talked about the PLCC model. I never explained what constant chromaticity is. Piecewise linear constant chromaticity. It implies that you don't have any channel interactions. But in fact, sometimes you do. And there's another model, more complicated, that can deal with that. And it's called the PLVC model, the piecewise linear variable chromaticity model. But I don't have time to talk about that. But in this case, we've got a small discrepancy between the measured white and the predicted white, and that's a measure of channel independence. Clearly, the smaller the delta E here, the better. And then finally, I'm looking at spatial independence. So we might put a grey patch on a black background and a white background. And the two greys should be identical. So I'm not talking here about what they look like. Obviously, the grey on the right-hand side would look darker than the grey on the left-hand side because of contrast. That's not what I'm talking about. If you measure this grey and that grey, you should get the same XYZ values. The fact that one looks darker is a property of your visual system. But in fact, you should get the same XYZ values if what's happening in this part of the screen has no impact on that part of the screen. In other words, we have spatial independence. Unfortunately, because of the electronics of displays and other factors, good quality displays have very good spatial independence. Cheaper, lower quality displays have poor spatial independence. In this case, you can see we've measured or quantified the spatial independence as 0.2 C-lab units. So summarizing then, we have this thing that color characterization is a two-stage process. It is simple, but conceptually there are a few things there that are a little bit you need to get your head around. The two steps are, we start with RGB, which are the numbers we're putting into the computer to drive our display. Our first step is normalization and linearization to produce normalized, linearized RGB values. And we do that using the GOG model, for example, or the PLCC model, my preference. We normally do it with red, green, and blue color ramps. It is also possible to do it with a grayscale rather than using the individual color ramps, but it's slightly more complicated conceptually. And then the second step is, once we have the linear RGB values, we have this matrix M, which we can simply write down once we've measured the primaries at full strength, and we can use that matrix to convert RGB into XYZ with simple matrix multiplication. So I hope you found that interesting. If you want to know more about it, you can email me at one of these two email addresses, or if you simply want to show me the data you measure for your display and perhaps it's not working quite as you think it should work, or you're having some problems with your code, by all means just email me. I'm always happy to talk to anyone about any aspect of color, certainly this sort of thing. And if you're interested, I wrote a book. This was the second edition in 2012, so it is 13, 14 years old now, but I think it's still reasonably in good shape. And that has a whole chapter on how to characterize displays, and other chapters on how to, for example, characterize cameras or printers. So thank you very much, and hope you enjoyed it.